Okay, so let's move on to the second talk by Surajit Bera from IISc, and he would be talking about Renyi-entanglement entropy in Hubbard model within DMFT.
I would like to thank organizer for giving me this opportunity to talk about my work on this topic, Renyi-entanglement entropy in Hubbard model within dynamical many-field theory. I also thanks my collaborator Sumantra, Surajit. Okay, we heard about the quantum entanglement in the previous talk. Let's just begin from my perspective. The quantum mechanics, the strange aspect of is are superposition, measurement, etc. But probably the strangest is actually the quantum entanglement. For example, you take a well-paired state, which is superposition of 0 and 1 plus 1 and 0. So there, the two qubits actually perfectly correlated. This is kind of two quantum correlation. So there is a various measure of entanglement, but one of them is popular one is entanglement entropy. So for that, what actually you do, you take a system and you divide the two parts A and B, and then for any state which is actually described by some density matrix that can be pure or mixed, you then calculate the reduced density matrix for subsystem A, which is basically you testing the degrees of freedom in the other parts of the system. And then this is the definition of von Neumann entanglement entropy, which is basically trace of A rho A log rho A. And similar, there is a definition of Renyi entropy. So these are things, and the n tends to 1, actually 1 goes to that. So we understand what is quantum entanglement, but why actually we care about in the condensed matter perspective. The reason is actually that we can characterize the various symmetry broken state, critical and topological ground state by this entanglement measure. Typically, the ground state have the entanglement in area law, plus there is a correction. This correction actually is important. That actually kind of characterize different kind of ground state. For example, you take the topological ground state where there is a area law and then there is a negative contribution constant that is topological called entanglement entropy, which is kind of define the topological order and one way to detect also topological. And so also in the context of MBL, the dynamics of entanglement, and also we had just the entanglement transition in the previous talk. So this is important in the condensed matter perspective, quantum entanglement. Okay, then how do we compute the entanglement entropy? So that is actually the important question. So it is in general difficult to compute entanglement entropy. For a non-interacting system, there is actually simple approach, correlation matrix approach. Then you can calculate the entanglement entropy. But for interacting system, there is exact diagonalization and density matrix renormalization group and quantum Monte Carlo method are there. But they have their own limitation, either in the system sizes or they are heavily numerical, and or you may have actually this conformal field theory, which are very sophisticated. So we need a general quantum many-body approach to compute Renyi entropy. The usual approach is the replica approach, which is developed by Cardi and Calabrese, which actually kind of have this complicated boundary condition. Here actually you are seeing that for third Renyi entropy, the degrees of freedom in the A have the antiperiodic boundary condition in the 3 beta range. Beta is inverse temperature, and then their B subsystem has beta antiperiodic boundary condition, and then you have to join A and B degrees of freedom properly. So those complicated boundary condition actually can be simplified. This actually a new path integral method actually that is developed in our earlier work with the Surajit and Sumantra. So where this complicated boundary condition basically simplified by introducing this kick term at the A subsystem at some imaginary time tau naught, and the boundary condition is a simple antiperiodic boundary condition on both fermionic fields. So it is now actually kind of simplified stuff, at least in the in terms of path integral. So let's actually calculate actually those thing for the interacting harmonic system. We took actually the Hubbard model for this case. We can formally write the path integral e to the minus, this is for second Renyi entropy. You write the path integral this, and the action has now the extra term, kick term. That kick term is coming here, and the expression of this kick term is actually this. I am not going to talk how it comes. This is there in this paper in earlier work. So this kick term introduced, as I said earlier, at tau naught in the A subsystem and non-zero in the A subsystem only. So far so good, but how do we actually extract this Renyi entropy? So the path integral is okay, but the extraction of this Renyi entropy is not so, because as you see that it actually turns, it is actually, if you write actually this term, so it turns out the log of Z2, and that is second grand potential, and log of Z usual thermodynamic potential. So those thermodynamic potential, their calculation is actually quite difficult. So it is not easily, you can easily extract from the thermodynamic potential, but we find a novel way to extract actually this thing by integrating the strength of kick term. You can actually compute actually this Renyi entropy, and this kick term again actually you can write very simple expression. It is sum of some on-site gains function in the subsystem only. So now the problem becomes to computation of this actually gains function within some approximation. So the one way actually we do usually treat the interaction is in condensed matter is dynamical mean field theory, which basically converts your lattice problem to a impurity problem in a self-consistent path. So that is the thing. So as a first attempt actually to implement actually this method, we actually use this iterated perturbation theory as impurity solver. But this actually method is general. You can use more sophisticated impurity solver like continuous time, quantum Monte Carlo, etc. So now you have to solve actually this dynamical mean field theory non-equilibrium. Of course, you have to do this imaginary time discretization. So you discretize the action in the imaginary time and you calculate the numerically. So you can't actually strictly do calculation in the t equal to 0. That means beta the inverse temperature infinity. So you can't do. So for that you have to calculate this as a finite temperature second Renyi entropy, and to get the entanglement you have to extrapolate at the t equal to 0. So first, we have to actually just some comparison with the exact diagonalization in the 1D Hubbard model. So this is for system size 6. In the left hand side, it is for subsystem size 1, and the right hand side, it is for subsystem size 2. So as we see at the high temperature, they actually matches quite well, but at the low temperature for subsystem size greater than 1, it have difference. That the reason is actually that ED and dynamical mean field theory have actually kind of different spectral function, very different spectral functions for small system. But we compare this actually QMC. That QMC data is taken from this actually reference, and as we see that the comparison with the QMC actually quite good, even in the 1D case. Actually, there is some recursive method. Actually, using that we can actually do we can go to very large system. Here we compute actually compute 100 system size, 50 system size. Also there is actually spin, so that actually you have to remember. So this is for temperature t equal to 0.2, quite relatively high temperature. Then we decrease the temperature. So at the high temperature you see the linear feature, and so that means your Renyi entropy have more actually thermal contribution, because thermal entropy follow the volume law. In the x-axis, it is actually subsystem size, and as you decrease the temperature, so the linear feature actually changes to actually the arc-like feature. So that actually that is actually kind of signature of more entanglement contribution in your actually Renyi entropy. So there is a kind of crossover from thermal to entanglement actually happen. So, but the question is how actually you disentangle this thermal and entanglement contribution, and also what is the scaling of this subsystem size Renyi entropy, and how interaction affects all those things. So the scaling formula for from CFT actually we know that Renyi-entanglement follow this logarithmic scaling with subsystem size, and for free Fermi system actually they follow this actually scaling, and where the central charge actually is 1, but we need some finite temperature formula that also is known in the context of CFT. So where that is logarithmic of sine hyperbolic, instead of sine function it is sine hyperbolic. So this says that the extrapolation to t equal to 0 not linear, it follows this actually log of sine hyperbolic, this non-trivial way it goes to t equal to 0. So now question is, this is actually CFT, and free Fermi system actually follows this kind of thing, but is dynamical, in the context of dynamical mean field theory, the metallic phase follow this kind of scaling or not? So that is the question that actually will actually answer. So this is I am showing for system size 50, where you feed that crossover formula, that log of sine hyperbolic function, and it shows that the fitting actually is kind of reasonably well, and you extract the central charge C, and so that central charge actually I plotted as a function of temperature. As you actually decrease the temperature, so different plot actually for different interaction strength, as you actually see, okay. As you see that as you decrease the temperature, that central charge actually slowly going towards the CFT value. Also with system size also it is actually the same trend. I have not shown here. So now actually we want to do more in the higher dimension, and also ask the similar question, what is scaling and etc. So in metallic phase, the scaling scaling we know for 1D, that is just this scaling, but for higher dimension there is a Wiedom formula. So the essential idea is actually that your finite Fermi surface is thought of as a collection of 1D gapless mode. Then the scaling is actually simpler. So you have 1D scaling, and then there is a number of effective 1D mode. So that actually basically depends on the relative orientation of both real and momentum space geometry. So this is the Wiedom formula. So now we'll actually see whether that actually fit our data or not. So we computed for a large system size 24 cos 24, and we also see that fitting also is kind of reasonably well. And for different temperature, we calculated different interaction strength. We calculated, and the central charge is plotted against this interaction strength. So the non-interacting value is this value, and as actually we increase the U, interaction strength is actually more, and we see that the central charge actually kind of substantially changes from the non-interacting value. So that is one difference from the 1D. Whether so now I can conclude my talk too. So basically in this work actually we developed a new path integral method to compute Renyi entropy. That is actually very general, and also we find a new way to extract the Renyi entropy very efficiently, that is kick term integration, which actually simplifies your boundary condition. And we show the computation within dynamical mean field theory approximation, and we show that the using the scaling that 1D DMFT Fermi liquid phase actually kind of well described by the conformal field theory. On the other hand, 2D DMFT, so there is a kind of signature that it is not so the case. In the future, actually, recent future, we'll do the same calculation in the MOT phase. There is 2D the MOT phase, and also we want to study the mutual information across the MOT critical point. Thank you for attention.
Questions?
Yeah, so sorry, this is something about the finite temperature. So at finite temperature, you have your state is a mixed state, right?
Yes. Yeah.
So which is why you are saying that you need to distill out the quantum entanglement from the quantum or the entropy of entanglement from the sort of.
Yes. In the mixed state, you always have there is a thermal contribution. So you need to go the zero temp T tends to 0. Then the thermal contribution will becomes very less, and you only have.
I see. So basically, in that sense, the results at finite T are not exactly the entanglement entropy of.
Yes, that's correct. But that scaling formula is kind of very important. So that actually you actually that kind of signals like the scaling of log of sine hyperbole, that free Fermi gas actually follow that formula. So then you know that T equal to 0, it should goes kind of CFT formula. So in the finite temperature, scaling itself actually signals whether your T equal to what kind of entanglement in the T equal to 0 state will be. T equal to 0 entanglement will be.
Yes.
But exactly we are not calculating in the T equal to 0 entanglement. So that is difficult with within this.
Actually, no, okay. You sort of answered that in your talk as well. So actually, then I just have a small question related to that, which is the 1D or sort of the free fermionic case is a CFT. But
Yes,
why does
that's
this
true.
result hold also for the interaction? Do you know?
No, because the entropy. So any actually Fermi liquid phase, the entropy actually kind of goes as a linear in the T, and free Fermi also gas. So basically, then actually you kind of there is a conformal mapping from the entropy to actually kind of this entropy to actually for entanglement. So there is a kind of you can argue from the entropy perspective, if it is go to linear in T, then you can actually argue that scaling formula is valid. Okay, I forget actually those parts.
Yeah.
So only interacting with cutting the liquid that also follows CFT.
It's a finite temperature CFT.
I see.
Yeah. That's
More questions? Okay. I just have a clarification in the slide that you showed this expression for this S-kick. Why is it local in space? I did not understand that. I mean,
now why it is actually in the only AF subsystem?
no. Okay, one more slide. No. Go forward.
Yes.
Go forward one more. Yeah. So this thing, why is it local in? So why GII enters there? I can understand why it's local in time, but why is it? Is there an easy way to understand why is it local in space?
Okay, I think. I think actually that okay. Actually these expressions. Okay, there is a delta I actually is sitting here. Yes, in this expression I forget to. So this actually is actually on site. So there is a delta ij sitting there. So this self energy kick actually is in the
Is actually
local.
okay. I don't understand.
Local.
Okay. Any more questions? Okay, if not, let's thank Surajit once more.